All right, I want to revisit the demo that we did in class last week, which was the standing wave demo. So I just want to play this, and I want to talk about what's going on in this demo and how it relates to harmonics. So let's watch this again. And so what you're going to see is the teacher here is going to change the frequency of the mechanical vibrator. And as he changes the frequency, right, different harmonics is what we call this. But essentially different patterns of waves begin to emerge. So we see here clearly a node, two antinodes. This is what we call the second harmonic. So as we're talking about standing waves, this is what I want you to think about. Of course, then we got up to I think you got up to the sixth harmonic, right, where it was vibrating and you got this pattern on the string. So keep this in mind as we talk about harmonics in this video. One of the things that's confusing, when we look at a wave on a string, on a slinky, we see it at one moment in time, it looks like this, right? And as we look at it in one moment of time, we see it going from here to here, but for a standing wave, it's actually going back and forth between this wave and this wave. And so when we draw standing waves, we draw them as these kind of egg-shaped waves. So one complete wave consists of two loops. Each loop then is half of a wave. I've talked about this in class, but I just want to make sure that everybody's clear on this as we kind of go forward. All right. So when we start looking at standing waves, we see a pattern emerge. So what we call the first harmonic in the simplest standing wave looks like this, right? This also, the first harmonic, is also known as the fundamental frequency. The second harmonic has two loops, or two half waves. Third harmonic has three loops. The fourth harmonic has four loops, and so forth. But what's interesting here is as the harmonics go up, the wavelength, take a look at this. Here is a whole wave, and it's on the entire length of the string. Well, here is now that same whole wave, but it's sharing the string with this other half wave, so this wave must be shorter than this wave. In fact, we're going to see something interesting here. Let's make the length of the rope that the standing wave is on. The entire rope is going to be 1 meter long. So it's the same rope for all of these. So the length of the rope is 1 meter long. So what we see here, and we can use this math here, if the length of the rope is 1 meter long here, and there's half a wave, then the wavelength of the first harmonic would be 2 meters long. We get to the second harmonic, and now this is 1 meter long, and a complete wave is on the 1 meter, so the length of that wave is 1 meter. We get to the third harmonic, and we'll have to think a little bit here, but now there are three half waves on the 1 meter string. So two half waves make a wave. So the wavelength in this case, the easiest way to think about this is each half wave must be 0.33. Since this is 1 meter, then that's 0.33, that's 0.33, and that's 0.33. Then a whole wave would be 0.33 times 2, or 0.67 meters. We get to the fourth harmonic, and now we have four half waves. So the distance from here to here is half a meter, 0.5. In the fifth harmonic, we see there are now 2.5 waves on here. So then we simply we see here that we have 1 meter divided by 5 is 0.2. So each half wave is 0.2. So a complete wave on this rope would be 0.4 meters. And then to the sixth harmonic, there are 6 of these. So each wave is 0.66, or sorry, 0.166. So a whole wave here would be 0.33 meters. So what's interesting, a couple things. Qualitatively, we see as the harmonics increase, wavelength decreases. Additionally, we can see a relationship here. If you take the fundamental frequency and you know the wavelength of the fundamental frequency, let's say it's 2 meters, the second harmonic is 1 meter. Well, you can take the wavelength of the first harmonic and divide it by 2 and you'll get 1. If you take the wavelength of the fundamental and divide it by 3, you get 0.67. If you take the wavelength of the fundamental and divide it by 5, 2 divided by 5 is 0.4. 2 divided by 6 is 0.33. So we have a mathematical relationship that the wavelength, and we see that relationship below. Furthermore, watch this. If I arbitrarily say the wave speed on this string is 1 meter per second, and I could do that because on a string the wave speed is determined by the type of string, how thick it is, and how tight the string is. So let's just say the wave speed is 1 meter per second. It's constant throughout. I'm going to fill out this chart for the frequencies that would happen using we remember our wave equation, which is frequency times wavelength equals wave speed. And watch what happens when I do the frequencies. When I follow this equation and I fill in the frequencies for each of these, look what happens. It's great. As my harmonic increases, the frequency increases. So we could say that the harmonic number is proportional to the frequency number. Not only that, but if I double, so first harmonic, the second harmonic is twice the first harmonic. Well, the frequency of the first harmonic is twice that of the fundamental frequency. The fifth harmonic is 5 times the fundamental frequency. So if you know the fundamental frequency, you know any of the harmonics. It's awesome. All right, so let's check your understanding with a few quick little questions here. And pause the video so you can think about this. But go ahead and read this question and see if you can come up with the right answer. All right, so here's the situation. We've got a 1.2 meter, not meter, but we have a 1.2 meter string. We've got the first, second, and third harmonic, right? So the number of the harmonic is the number of half waves we have. It says determine the wavelength. So I see here for my first one, the wavelength, I have half a wave, so the wavelength would be 2.4 meters. Here my wavelength, I have a whole wave, so that's 1.2 meters. That one's easy. And then my third one, now I have three half waves. So this is going to be 0.4, right? So I take 1.2 divided by 3. Each half wave is 0.4, so then my wavelength is 0.8 meters. Let's try another one. All right, so here's another question. So here we have a string, 1.5 meters long. So what harmonic is that, by the way? You should have said the first, just like physics, number 1, right there, first harmonic. The string vibrates up and down 33 complete cycles in 10 seconds. So it says determine the frequency, period, wavelength, and speed for this wave. So take a minute, pause the video, see if you can do this, and let's reconvene and answer the questions. So to answer these questions, so the frequency, if this goes up and down 33 times in 10 seconds, right, so that's 33 waves in 10 seconds, the frequency is 3.3 hertz, so there's that one. A period, remember, is 1 over the frequency, a very useful equation. So we just do 1 over the frequency. We get a period of 0.303 seconds. Wavelength. Now, we can think about this here. This is 1.5 meters, and it's half of a wave. So then that means a whole wave would be 2 of these, which would be 3 meters long. So that's where we get the wavelength. And then our speed is frequency times wavelength. So the frequency, 3.3 hertz, times our wavelength of 3 meters, gives us a speed of 10 meters per second. So hopefully that makes sense. And I've got one more if you want to give it a try here. Very similar to the last question, but here we have this wave, 6 meters long, and it's asking us to find the frequency, period, wavelength, and speed. So go ahead and pause the video give it a crack and see what you do, and we'll check the answer here. And here are your answers for this one. So hopefully you're able to get everything there. If you have any questions, as always, send them my way, and I hope you had fun.